Yes, Mr. Millett.
Yes, Mr. Chairman. Good afternoon. Good afternoon, members of the panel. This afternoon, Professor Luke Bisby will give an oral presentation based on his experimental work. Before we call him, we should give a trigger warning for those who are watching. Several of the slides in Professor Bisby's presentation contain images and videos of fires, so it's important to warn anyone watching who would prefer not to view that content. So, without further ado, may I please now call Professor Bisby?
Yes, thank you very much. Good afternoon, Professor Bisby. Welcome back. You're going to make the affirmation, I think.
I am.
The words are on the screen then. Would you read them out, please?
I do solemnly, sincerely, and truly declare and affirm that the evidence I shall give shall be the truth, the whole truth, and nothing but the truth.
Thank you very much. Would you sit down and make yourself comfortable? Yes, Mr. Millett, when you're ready.
Thank you, Mr. Chairman. Professor Bisby, welcome back to the inquiry, and thank you very much for attending again to answer questions and present your expert opinions. It's right, I think, that you've produced 6 reports for this phase 2 of the inquiry, 3 of which we will deal with next week when you come back to give evidence, and 3 of which I think we'll be hearing from you about this afternoon during your presentation on the experimental work that you've conducted. Can we please go to LBYWP 1702? LBYWP 1702. Now that is a report entitled Work Package 1 Regimes of Burning, dated the 15th of March 2020. If we go, please, to at the bottom of the page, we can see a signature, or middle of your screen. Is that your signature?
Yes, it is.
And I think it was updated on the 1st of June 2020, as you can see. If we go to page 17 of that report, you can see there, section 2.5, statements. And if you go to page 18, we can see a signature. Is that your signature, if we turn the page? Is that your signature there?
Yes, it is.
Are these statements, are these your statements as to this report?
Yes, they are.
And that is your signature, as you've confirmed. Have you read this report recently?
I have.
And yes. Can you confirm that the facts and matters, the factual matters set out in the report, are true to the best of your knowledge and belief?
I can.
And can you confirm that the opinions that you've given in this report are your honestly held professional opinions?
I can.
And is it true that you provided your expert opinion in this report to the inquiry in the same way that you would have provided it to an English court?
That's correct.
Thank you. Now let's go next, please, to LBYWP 2701. LBYWP 2701. This is your report entitled Work Package 2 System Interactions, and there's a signature above the date of the 15th of December 2021. Is that your signature?
Yes, it is.
And if we go, please, to page 14 of the report, you'll see section 1.5 at the foot of the screen, and there are statements there set out, and then they continue over the page onto page 15. Are those your statements there as to this report?
Yes, they are.
And have you read this report recently?
Yes, I have.
There's a signature at the bottom. I'm assuming that that's yours, yes?
Correct, yes.
Yes. And can you confirm that the facts and matters set out in this report are true to the best of your knowledge and belief?
Yes, I can.
And that the opinions that you've given in this report are your honestly held professional opinions?
Yes, they are.
And is it true also that you've provided your expert opinion in this report in the same manner that you would have done had you been asked to provide it to an English court?
That's correct, yes.
And lastly then, please, if we can turn to LBYMT 702, LBYMT 702. This is a report entitled Materials Testing Report 1, dated the 24th of February 2019, updated on the 1st of June 2020, with a signature in the middle. Is that your signature?
Yes, it is.
And I think that report is to be read in conjunction with your final Phase 1 experts report. Is
That's
that
correct.
right?
Yes.
Yeah. And if we go to page 9 in this report, please, you'll see section 1.5. That's also bearing the title Statements, and you can see the statements there in 4 paragraphs, 48 to 51, with a signature below it. Is that your signature?
Yes, it is.
And are those your statements?
Yes, they are.
And have you read this report recently?
I have.
And can you confirm that the facts and matters set out in this report are true to the best of your knowledge and belief?
Yes.
And that the opinions contained in it are your honestly held professional opinions?
Yes.
And is it true, again, that you have provided this expert opinion to the inquiry in the same way that you would have done, if asked to do so, to an English court?
That's correct, yes.
Can you also confirm that none of the opinions and conclusions in your reports that I've shown you have changed since they were produced?
That's correct.
And today I think you're going to give us a presentation on these three reports. Can you confirm now that the facts and opinions that you express in your presentation are true so far as the facts are concerned, and your honestly held opinions so far as they are matters of opinion?
That's correct.
Thank you very much. Professor, we look forward to hearing your presentation.
Thank you very much. When you're ready, yeah. Good afternoon, sir, members of the panel. Thank you very much for inviting me to give evidence today. And good afternoon, Mr. Millett. To begin my evidence today, I'll deliver a presentation that I've prepared based on my Phase 2 instructions from the inquiry. I've scripted my presentation, so I'll be reading from a script, so as to keep myself to time and to avoid me getting a bit too interested, perhaps, or dwelling for too long on some of the finer technical points. It's my expectation that this should take me about an hour and a half to 2 hours to complete, perhaps slightly longer if there are any immediate questions that need to be dealt with as we go. You've already received copies of my Phase 2 reports. These can be broadly characterized as my experimental reports, which I'll discuss today, and my regulatory and testing reports, which I understand we'll deal with next week. My experimental reports consist of my materials testing report 1, my work package 1 regimes of burning report, and my work package 2 system interactions report. My regulatory and testing reports consist of my regulatory testing and the path to Grenfell report, my BRE reconstruction report, and my BR135 desktop assessment report. Now, the time available for my presentation today doesn't allow me to cover all of the ground contained within these 6 reports, obviously. It's my intention this afternoon to focus on my experimental reports. And I'll do this in 3 parts as outlined here. I hope to summarize, illustrate, and explain in brief what I've done, why I did it, what I found, and what I think it means. I understand that Mr. Millett may then have some questions for me, both on this work and on my other reports, next week. I hope it goes without saying that I'd welcome questions or discussion at any point during this presentation, so please don't be afraid to interrupt me if something does come up that causes confusion, rather than waiting until I've finished. Now, I'll move firstly to part 1 of my presentation. Now, as it's been almost 4 years since I last delivered a presentation to the inquiry, I'd first like to summarize some important background and context for my work. My Phase 2 instructions asked me to prepare reports on the performance and respective contributions of the materials and products which formed parts of the exterior of Grenfell Tower to the initiation, growth, and spread of the fire. This was to include a program of experimentation aimed at understanding and quantifying the respective roles of the various materials and products that made up the cladding system at Grenfell Tower under a range of relevant fire conditions and system geometries. I'd like to begin my presentation by quickly summarizing what I understood when I embarked on this work back in the second half of 2018. At that time, my understanding was based on evidence already available from Phase 1 of the inquiry, as well as on my own knowledge and professional experience. I understood that the fire at Grenfell Tower started on the 4th floor in the kitchen of flat 16. I understood that the ventilated rain screen overcladding system that had been installed on Grenfell Tower incorporated a large number of combustible materials and products. Most notably, this included the aluminium composite material, or ACM, rain screen product Renabond PE with a polyethylene polymer core, foil-faced PIR and phenolic foam polymer insulation products, and aluminium-faced window infill panels with an extruded polystyrene core. I understood that burning of materials and products within the external wall assembly and within Grenfell Tower's architectural crown led to the rapid and uncontrolled fire spread up, down, and around the building on the night of the fire. I understood that the fire exited the kitchen of flat 16 and spread to the external cladding. I expressed an opinion at that time that the precise manner in which the fire spread from inside the kitchen out and into the cladding was most likely by a combination of two routes. During my June 2018 presentation, I showed you this slide, which shows the kitchen window of flat 13 after the fire. And the geometry of the external wall arrangement here outside flat 13, as far as we can know, is essentially the same as that which was present outside the kitchen window of flat 16 at the time of the fire. I took a horizontal section through the external wall at that location, shown here with a dashed line, and I zoomed in on the highlighted region here, where the windows meet the columns. On that basis, I developed this sketch of the materials, products, and geometry that exist at this location, and I noted that one potential route for fire spread to the cladding was through the side of the window and into the back of the cladding cavity. This could occur due to parts of the internal window surround and external cladding system being penetrated by the fire, essentially with the fire entering the cladding around the side of the window frame. In this case, the fire enters the cladding from the rear, but then finds a layer of polymer foam insulation facing a Renabond PE ACM rain screen with a ventilated cavity in between them. I also developed a sketch through this vertical section of the kitchen window of flat 16, highlighting this region of the external wall. The resulting sectional sketch that I developed on this basis is shown here, where the other most likely route of fire spread can be seen essentially like this. This consists of fire exiting the kitchen window or the extract fan panel, which was within the kitchen window, with flames and hot gases impinging on the cladding directly above the window. Again, as the fire enters the cladding, it finds a layer of polymer foam insulation facing a Renabond PE ACM rain screen with a ventilated cavity between them. At that time, I was unable to definitively say which of these was the dominant route for fire spread to the cladding. My opinion remains that some combination of these two fire spread routes caused the initial ignition that led to sustained burning and escalation of the cladding fire. During my phase 1 work for the inquiry, I closely examined the materials and products within the external wall arrangement at Grenfell Tower. I concluded that the available evidence strongly supported a hypothesis that the presence of ACM panels with a polyethylene core material over large areas of the external surface of the tower was the primary cause of upward, downward, and horizontal fire spread. I observed that the Renabond PE incorporated a highly combustible polyethylene polymer which melts, drips, and flows whilst burning at elevated temperature. I stated that this polyethylene material should be expected to release large amounts of energy during combustion, to rapidly lose its mechanical properties on heating, and to cause separation of the ACM rain screen panels. I also considered the evidence concerning the role of the combustible insulation products in terms of their contribution to fire spread on the exterior of the building. I stated that the available evidence was inconclusive regarding the extent to which the presence of combustible insulation products within the rain screen cavity contributed to the rate and extent of upward, downward, and horizontal fire spread. I found that pyrolysis and charring of the insulation products had occurred during the fire, and that exposed surfaces of polymer foam insulation were present within the cladding system before the fire. Without wishing to preempt the remainder of my evidence, I'd like to confirm that my views on these matters have not changed. At that time, I considered it more likely than not that the presence of the insulation products contributed to some extent, although I wasn't able to quantify this contribution. Whilst I was satisfied that the Renabond PE was primarily responsible for the fire spread, I had outstanding questions about the roles and contributions of the other products used within the external wall arrangement, the polymer foam insulation products in particular. During my phase 2 work for the inquiry, I undertook to better understand and demonstrate the potential contributions of the various products to the rate and extent of fire spread. I performed a series of experiments in 2 work packages, which I've referred to as Work Package 1, Regimes of Burning, and Work Package 2, System Interactions. First, in Work Package 1, I performed experiments to demonstrate and understand how these products responded to heating and burn in isolation. This was necessary both to underpin my own understanding of the thermal and mechanical properties of the products under a range of representative heating conditions, and to ensure that the inquiry is given rigorous scientific data upon which to base its eventual conclusions. Second, in Work Package 2, I performed further experiments aimed at understanding how these products burned as part of a system and how their individual burning behaviors might lead to interactions within a ventilated rain screen cladding system. All of the work that I'll present today was completed under my supervision at the University of Edinburgh. I was assisted by a team of colleagues at Edinburgh, Dr. Rory Haddon, Dr. Simon Santamaria, Mr. Michal Krejcevic, Mr. David Morissette, and Dr. Angus Law. I'll mostly use first-person singular language in my presentation today, but it's very important for me that I highlight the significant contributions that were made by all of these individuals. Under instruction from the inquiry, much of this work was also performed in close consultation with Professor José Torero, who also witnessed many of the experiments and participated in our analysis of the results. In performing this work, I was faced with a choice. Should I experiment with products that were taken from Grenfell Tower after the fire? Should I experiment with products that were taken from Grenfell Tower after the fire, or should I use pristine materials and products provided to me by core participants to the inquiry? I was concerned that products from the fire scene might have been damaged during installation, the fire itself, or removal, and that obtaining a sufficient quantity of undamaged products could present a challenge. I was also aware that the Metropolitan Police Service were intending to use products taken from Grenfell Tower for the purposes of both standard fire tests and fire reconstructions, and that the availability of undamaged products from the tower might become limited. I decided, with the support of the inquiry, to seek pristine proxy product samples directly from core participants. I'm grateful to these core participants for providing the requested specimens in a timely fashion. To satisfy myself that the products provided to me by the core participants were, in fact, the same in all material ways as the products that had been installed on Grenfell Tower, I undertook my own due diligence diagnostic testing. This was done by comparing against small samples of undamaged reference material of products taken from the tower, and these were provided to the inquiry by the Metropolitan Police Service. These diagnostic tests confirmed the similarity of the proxy products that I was using to those present on Grenfell Tower at the time of the fire. So in the first half of my presentation today, I'll describe and discuss the comparatively straightforward Work Package 1 and its results, before moving on to what I consider to be the more interesting and complex results of Work Package 2. I began Work Package 1 with an overall expectation of how each cladding product would perform under heating. This was based on my knowledge, experience, and a physical understanding of the reaction to fire behavior of various types of materials and products. Work Package 1 focused on the behavior of the following 4 products, and I'll explain why I chose these 4 products as I go. Renabond PE ACM, or aluminium composite material, which is shown here. In basic terms, this product consists of 2 0.5 millimeter skins of aluminium, either side of a 3 millimeter thick core of polyethylene. Celotex RS5000 insulation board, which is shown here. I'll refer to this simply as RS5000 throughout this presentation. This product consists of a polyisocyanurate, or PIR, polymer foam core, faced on both sides with a thin, unperforated aluminium foil, which is only a fraction of a millimeter thick. I've performed experiments on both the 80 millimeter thick RS5080 product and the 100 millimeter thick RS5100 product. Kingspan Cooltherm K15 insulation board, shown here. I will refer to this simply as K15 as I go forward. This product consists of a phenolic polymer foam core, faced on both sides with a thin aluminium foil, which again is only a fraction of a millimeter thick. The aluminium foil facer in this case has small perforations in it, which if you look very closely at this picture, you can see as small dots on the foil's surface. And finally, Aluglaze window infill panels, shown here. And this product consists of 2 flat aluminium sheets, each 1.5 millimeters thick, with an extruded polystyrene, or XPS, polymer foam core, which is 25 millimeters thick. So these are the 4 main products that made up the refurbishment cladding system at Grenfell Tower. Obviously, there were other products involved, but these are the 4 main products that I've considered. It's worth noting that PIR and phenolic foams are both thermosetting polymers, whereas polyethylene and XPS foam are both thermoplastic polymers. And I've discussed those issues before, and I'll demonstrate the key differences between these two classes of polymers during my presentation today. I've provided more detailed descriptions of all four of these products in my Phase 2 reports, so I'm going to avoid any further description here, and we've been talking about them for many years now. In my first presentation to the inquiry, and indeed this morning, Professor Torero also covered a lot of this ground, I described some fundamental fire science concepts and terminology, including detailed discussions of pyrolysis, thermal inertia, flammability, ignition, heat of combustion, heat release rate, and flame spread. And those are all really centrally important concepts, as Professor Torero illustrated this morning. I'm not going to rehearse those concepts here again today, but the concepts that I covered during my presentation in 2018 are all immediately relevant to what I will present today. I believe that the most useful and illustrative way for me to present the outcomes of my experiments to individuals who are not fire safety specialists and who may not have a deep technical understanding of all of the terminology that I've just listed is by walking through some videos of selected experiments and describing my observations as we go. And I'll do quite a lot of that today, starting in a few minutes. However, before presenting the experimental apparatus and the procedure that forms the core of my Work Package 1 experiments, I think it's useful to frame the discussion in terms of some of these fundamental reaction to fire properties or behaviors of the four cladding products of interest. Now, when we think about the reaction to fire of a material or a product, we need to consider a range of interrelated questions. How easily is it ignited? Under what conditions will it continue to burn once ignited? Will it spread flame over its surface, and under what conditions? How much energy, i.e. heat, is released when it burns under the conditions of interest? And at what rate is that energy released? Answers to any one of these questions in isolation cannot tell the whole story of the fire hazards presented by a material or product. Indeed, this is why I routinely use the word Bernie as a catch-all term describing hazardous with respect to fire. None of the other descriptors, combustible, flammable, ignitable, etc., adequately describe fire hazard on their own. And this is also why my Work Package 1 report, and indeed my other experimental reports, contain results from a number of experiments conducted at various scales and under a wide range of heating conditions. So first, I'd like to consider the heats of combustion of the polymer core materials from my four products of primary interest. As I explained in my 2018 presentation to the inquiry, the heat of combustion of a material is a measure of the total energy that can be released per unit mass of the material when burning under optimal conditions for combustion. The heat of combustion thus provides an upper limit on the amount of energy that could be released by the burning of a material. You'll hopefully have noticed that I'm using the word material determinedly in this context rather than product. Products do not have heats of combustion, unless, of course, a product is made entirely of one material. And so that's why I'm using that terminology. Only materials have heats of combustion. This slide shows a comparison of the heats of combustion that were measured for polymer core materials from each of the four products of interest. They were measured using a bomb calorimeter, and it's clear that the polyethylene core material from the Renabond PE, the leftmost bar, has the highest heat of combustion, and that's comparable to diesel fuel, as has been mentioned numerous times throughout the inquiry, and that the phenolic foam from the K15 product has the lowest of the products I'm showing here. However, it's important to recognize that these values are given in a per unit mass of the core material basis rather than a per unit area of the product that incorporates it basis. If I multiply these heats of combustion by the densities of the respective core materials and then by the thicknesses of core material within each product, I get the maximum possible energy contribution per unit area of each product, which is actually a more useful metric, i.e. the maximum energy that could be released if the product were to burn under optimum conditions. And this comparison is shown here. We can see that on this basis, the story changes. because it's not simply a question of how much energy is in the material per unit mass, but also how much mass of material is present within the product. By this comparison, we can see that the maximum amount of available energy per unit area becomes more comparable between the Renabond and the polymer foam insulations, and that the Alu-Glaze window infill panel the Alu-Glaze window infill panels appear to be less significant. But we then need to ask another question. How much of each product, in terms of square meters of surface area, was present on Grenfell Tower before the fire? Based on the design drawings for the external wall arrangements, I've calculated the total surface area of each product on a typical single story of Grenfell Tower, as shown by this highlighted area. We then end up with an approximation of the maximum possible energy contribution from each of the 4 main cladding products that were actually installed on Grenfell Tower. Here, I'm assuming as a worst case scenario that all 4 products burn entirely, and that this burning occurs under optimal conditions for combustion, which is actually not a fair comparison, I should say. Here we can see that the result of this calculation for a single story of Grenfell Tower, if we assume that only Celotex RS5000 insulation was present, i.e. there was no Kingspan present, and it was all the Celotex product. But we would see an almost identical story if we assume that only Kingspan K15 was present, and I've outlined that graph in my Work Package 1 report. In any case, this plot shows that the maximum potential energy contribution from the Alu-Glaze window infill panels is small when compared with the Renabond PE or the polymer foam insulations. And for this reason, I'll not discuss Alu-Glaze window infill panels much more within this presentation. However, my Work Package 1 report does contain results of experiments on Alu-Glaze window infill panels, and I do consider that these are relevant to cladding fire safety issues, particularly for other buildings whose exterior walls and window sets may contain similarly hazardous products. Now, of course, the comparison in this plot is only fair if we assume that all of the energy that is available within each of these products is actually released during a fire. And this is extremely unlikely in a real fire, both because the combustion environment in a real fire is not optimal, and because of the differing physical responses of the polymer core materials that are involved. The thermoplastic core materials in Renabond PE ACM and in Alu-Glaze window infill panels will melt and drip, whereas the thermosetting polymer core materials of RS5000 and K15 will char. They do not melt and drip. I'll show you how these differences affect the respective products' burning behaviors later on in this presentation. In any case, the maximum potential energy contributions on their own don't provide any information regarding the rate at which energy would be released after a product is ignited, or indeed the total amount of energy that would actually be released in a real fire. Nor do the preceding comparisons account for the heat transfer processes that lead to ignition, the material geometry, or the physical changes that may occur, all of which will also affect a product's burning behavior. To illustrate and understand these other factors, we have to perform other types of experiments. For my Work Package 1 experiments, we designed and built a bespoke experimental apparatus. This was designed to investigate the mechanical behaviors of the products when subjected to a range of heating conditions, their characteristic burning behaviors, the impacts of sample scale and localized heating, the impacts of fixing and support conditions, and to establish the heat flux causing ignition of the various products of interest when tested under specific conditions of heating and fixing. I'll now give a basic description of my Work Package 1 apparatus. This was used to heat samples, essentially, of the 4 products of interest under carefully controlled and repeatable conditions, and to study their thermal and mechanical responses. Now, this photo shows the heater that we used in our experiments. It consists of an array of radiant panels that are fueled by a precisely controlled flow of propane gas mixed with air. The radiant panel array was mounted onto a motorized actuator, which allowed the distance between the panels and the samples to be varied, as I'll show you in a moment. So it moved in that direction. This allowed us to control the severity of heating, which we call the heat flux, as Professor Torero explained this morning, and which is measured in units of kilowatts per meter squared, so units of energy per time per unit area. To give you a sense of scale, this rig that I'm showing here is about 1 meter tall. Experimental specimens were mounted onto a specimen holder, as shown here, and were held above a tray which was used to catch any falling debris. Both the specimen holder and the debris tray were placed on balances, essentially digital scales. And these were placed there to measure the masses lost or gained by the products throughout the experiment, or masses lost by the product or mass gained by the debris tray. The experimental arrangement also included other features that were aimed at improving consistency and repeatability of our experiments, including a pilot flame, a heat shield, and a movable heat flux gauge. These are all shown here and are described within my Work Package 1 report. The experimental specimens were square, flat samples of the respective products of interest with exposed edges of core materials, and these samples were either 100 millimeter square or 500 millimeter square. Renabond PE samples were tested in 3 different configurations, namely a rear fixing condition shown here, with the sample supported from its rear aluminium skin, thus allowing for downward mobility of the front face of the sample on heating, and hopefully it will become clear what I mean when I show you some of these experiments. The front view in this slide on the left shows the heated face of the sample. So the face on the left in that leftmost photo is showing you the face that was heated during the experiment. This photo also shows that we installed thermocouples on and within the samples to measure the temperatures of the aluminium facers and the polyethylene core material, and that supporting rods were welded to the sample's aluminium skins, as shown here in the right-hand image. We also used a front fixing condition, shown here, with the sample supported from its front aluminium facer, thus allowing for downward mobility of the rear face of the sample on heating. And finally, a through fixing condition was also used, with the samples drilled through and supported from both of their aluminium skins, the front face and the rear face, as shown here, thus preventing downward mobility of either of the aluminium skins and also restricting to some extent their mechanical separation on heating. These 3 fixing conditions were chosen so as to shed light on some of the observed differences in the performance of ACM products when exposed to fire in either riveted or cassette configurations that we've heard something about during this inquiry. And I've discussed that in some detail in my Work Package 1 report. For instance, to better understand the physical reasons why ACM PE products tend to perform better, for instance, in single burning item tests, when they're tested in a riveted rather than a cassette configuration. Insulation product specimens in our experiments for Work Package 1 were held in place, as shown here, using 2 steel rods that were inserted into the rear face of the samples. And in some cases, again, as shown here, the foil facer on the exposed face of the sample was removed prior to the experiment. We did experiments both with and without foil. This was done because during phase 1, I had identified locations within the cladding system where cut edges of insulation products were left exposed within cavities in the cladding system at Grenfell Tower. A large number of measurements were recorded throughout these experiments. These included multiple videos framed from different vantage points, the masses of the specimen and any debris falling into the tray beneath the specimen, as I've mentioned, the heat release rate, or HRR as we refer to it, which was measured using a technique called oxygen consumption calorimetry, which I won't go into today, and temperatures, as I've already mentioned, which were recorded using thermocouples. In a few minutes, I'll show you some videos of typical experiments performed using my Work Package 1 experimental apparatus, as I've described it here. And I hope that when I show you these videos, this will all become a bit clear. I can understand it's probably a bit difficult to get your head around what I'm talking about at the moment. So now let's turn to some of my main experimental results. Before a product can burn with a flame, it needs to ignite. Ignition is simply the initiation of sustained flaming. Whether ignition of a solid material occurs depends both on the severity of heating, which as I've mentioned, we call the heat flux, and the duration of heating. In my 2018 presentation to the inquiry, I also explained that flame spread can be thought of, if you like, as a series of ignitions. Thus, in attempting to quantify the relative contributions of the products making up the external wall arrangement at Grenfell Tower, it's important to understand and quantify their respective ignition characteristics. I performed a range of experiments to characterize the ignition behavior of the 4 products of interest, some of the key outcomes of which are summarized in this plot. On the vertical axis in this slide, I'm plotting the heat flux, again, the severity or intensity of heating in kilowatts per meter squared. Now, to put those values in context for you from 0 to 100 kilowatts per square meter, at the low end, exposure to a heat flux of 5 to 10 kilowatts per square meter is likely to result in skin burns in less than about 30 seconds. At the high end, a heat flux exposure of 75 to 100 kilowatts per square meter is in the range of the severities of heating that would be expected over the first 1 to 2 meters above the hearth in a BS 8414 large-scale cladding test, as Professor Torero mentioned this morning. It's noteworthy that all 4 of the products listed in this plot are metal-faced polymers, but that the thermal and physical properties of both the metal facers and the polymer cores differ substantially. And you can see I'm plotting results both with and without the aluminium facers. If I highlight the Renabond results, we can see that the Renabond PE product will ignite at comparatively low heat fluxes. This means that, in the configuration that we tested, it would be expected to ignite in most any cladding fire scenario. We can also see that the removal of the aluminium facer, moving from the red data to the blue without, makes the Renabond PE only slightly more susceptible to ignition, so not much of an effect. The same is true for the Aluglaze window infill panels, albeit with a slightly higher critical heat flux, both with and without the aluminium facers in place. However, there's the Aluglaze. However, the ignition behavior of the polymer foam insulation products, Celotex RS5000 and Kingspan K15, is drastically reduced by removal of the foil facers. Again, red with the foil facers and blue without. These products are both much more difficult to ignite when their foil facers are present, as we should expect. The foil facers reflect radiation, they alter the convective heat transfer conditions at the surface of the samples, and to some extent, they mitigate ignition and burning of the flammable pyrolysis products that are generated during heating.
Professor, I'm going to interrupt you for a second. I think the stenographer is finding it quite difficult to keep up with you. So if you could slow down a little bit, I think she'd find it.
I will certainly try.
Do you mind? I'm sorry.
Yes, apologies. Okay, yes. So the beneficial effect of the foil facers is less pronounced for the Kingspan Cooltherm K15 insulation. I consider it likely that this is at least partly due to the presence of the perforations in the K15 foil facers that are not present for the RS5000. I should also say here that I consider that the presence of perforations in the foil facers of a polymer foam insulation should, self-evidently, be expected to influence, by which I mean worsen, its reaction to fire behavior. I should also note that this plot fails to tell the whole story, because whilst it tells us what severity of heating will lead to piloted ignition eventually, it doesn't tell us how rapidly this ignition will occur at a given heat flux. In general terms, all other factors being equal, it takes considerably longer to ignite the polyethylene core of an ACM product than it does to ignite the polymer foam insulation without a foil facer. We're talking minutes for the ACM versus seconds for the polymer foam insulation when we take the foil away. And of course, all of this only says that a product will ignite and start to burn, doesn't tell us whether it will continue to burn, nor indeed whether it will burn quickly or slowly. To more fully understand the reaction to fire behavior of these products, we need to study their responses when subjected to intensities and distributions of radiant heating that are representative of those to which they might be exposed during a cladding fire. So now I'd like to show you some of our experiments so that you can see some of these interesting behaviors for yourselves. It's a shame that the chairman, members of the panel, and counsel to the inquiry weren't able, mostly thanks to the pandemic, to come to Edinburgh and witness any of these tests, as I really do believe there's no substitute for observing such things in person. For Renabond PE, I knew that samples would be comparatively difficult to ignite, as I've just shown, but that under high heat fluxes, they would be certain to ignite eventually. I knew that once ignited, the polyethylene would melt, drip, and flow, most likely whilst burning. I therefore knew that molten polyethylene could form pool fires. I knew that mechanical failure, or separation of the aluminium faces at comparatively low temperatures, when not mechanically restrained in place, for instance by rivets, would govern the fire hazard. And my experiments illustrated all of these expected behaviors, so there were no real surprises there. And I found that our well-controlled experiments were extremely repeatable, which was also comforting. I'll show you a brief video of a typical experiment on a sample of Renabond PE so that you can see how these experiments unfolded. I've made videos of all of my experiments available via the inquiry, and I've also produced a number of composite comparative videos that are available alongside my Work Package 1 report, and indeed are referenced within that report. Mr. Chairman, the video that I'm about to show probably warrants a trigger warning, given its stark depiction of the fire hazards associated with these products. So perhaps I'll just pause for a moment. So this video, actually two videos, will show an experiment on a 100 by 100 millimeter square sample of Renabond PE ACM supplied by Arconic. This was the rain screen product installed on Grenfell Tower, of course. The sample in this case is supported from its rear face and has thermocouples welded to its front and rear faces. You can see the sample, the radiant panel array, the pilot flame just above the sample, and the debris tray below the sample in these two images. And I'll continue to show both the close-up view and the more distance view as I let this play forward. In this particular experiment, the sample was exposed to a heat flux of 50 kilowatts per square meter, and you will have noticed in my report that we used heat fluxes of 25, 50, and 75 kilowatts per square meter in our experiments. This is essentially an experiment chosen at random to show you. This heat flux, 50 kilowatts per square meter, is broadly representative of that which would be experienced about 1.5 to 2 meters above the hearth in a typical BS 8414 large-scale cladding test. Well, I'll explain to you first what we will see, and then I'll show it to you and explain it as we go. So we will see, once I let this run, we will see the radiant panel array, which is to the right in these images, will move toward the sample. Our timer will start at the moment that the radiant panel array comes to rest in front of the sample. After about 30 seconds, we'll see pyrolysis gases visible above the specimen. Between 30 seconds and 1 minute and 18 seconds, the rate of production of pyrolysis gases will increase. At 1 minute and 18 seconds, ignition will occur at the top of the sample. Just a few seconds later, the front aluminium facer will completely fall away from the sample and land, whilst burning, in the debris tray. The rear aluminium facer, which is restrained on the holding rods, will remain in place, and it will stay mounted on the sample holder, as will the majority of the polyethylene core, and that will remain attached to the rear face. Flaming will then continue on the front aluminium facer, now in the debris tray, and discontinuous flames will become visible over the front surface of the specimen. Flaming will then become well established over the front surface of the exposed polyethylene core that remains on the sample, and burning droplets of polyethylene core material will begin to fall from the base of the specimen and land in the debris tray. The rate of burning droplet production will increase until there's a near continuous stream of burning polyethylene core material falling into the debris tray, And after about 2 minutes, the dripping will cease, as all the polyethylene will be gone, and burning will continue only in the debris tray as a pool fire. Eventually, all flaming will cease, and the experiment will be halted. So I'll now let it play, and it should pause periodically so that I can point some things out. And I should say that the computer that we're running this presentation off is struggling to keep up with the high-res videos, so occasionally the digital timer does something a little bit weird, but you'll get the impression, I hope. So you can see now there's some smoke, pyrolysis products coming off the sample in the right-hand view. And the rate of production of pyrolysis gases appears to increase as we step forward in time, as we would expect. Keep that playing. At 1 minute and 18 seconds, we'll see ignition occur at the top of the sample. There it is. And a few seconds later, at 1 minute and 22 seconds, the front facer of aluminium falls away from the sample and lands in the debris tray, and you can see that it's now flaming in the debris tray. The back face of the aluminium remains in place, held on the sample holder, and the majority of the polyethylene core material remains attached to that face of the sample. Flaming then continues on the front aluminium facer, now in the debris tray, and discontinuous flames become visible over the front surface of the specimen. And you can see here we've switched to a low exposure view in the left-hand side so that we can see things as the flames grow. By 1 minute and 30 seconds, flaming is well established over the front surface of the exposed polyethylene, and the first burning droplets of polyethylene begin to fall from the base of the specimen and into the debris tray. The rate of droplet production increases quite rapidly, and a continuous stream of burning polyethylene falls into the debris tray and increases the size of the pool fire. It's probably also worth having a look at the left-hand image, just the way the polyethylene is melting and flowing and dripping, which you can sort of make out through the flames. At 2 minutes and 9 seconds, dripping ceases, and flaming on the specimen then also ceases shortly thereafter. Between 2 minutes and 9 seconds and 4 minutes and 48 seconds, you'll see I'm running at 10 times speed now. The length of the flames from the polyethylene, which is still burning in the debris tray, gradually decreases until extinction occurs. The experiment is then terminated. I hope that we can agree that that looked like quite a lot of fire from actually quite a small piece of material. It's perhaps a bit tricky to visualize a 100 by 100 millimeter square sample of Renabond PE. I've brought a sample with me. To put it into perspective, this was the piece of Renabond that we tested in that video, and that's about the size of a beer mat or a drinks coaster, to put in perspective for you. So it's a piece like that. So not very much material at all. If you run the numbers, which I've done, you would find that a typical single-story column cassette from Grenfell Tower, so a single panel of Renabond PE taken from the tower from one of the column sections, would contain about 270 of these in a single column cassette. Now let's take a look at some of the resulting data from this experiment. I'm going to focus on the data from this specific experiment. and then provide you some general conclusions and data afterwards. I mentioned previously that during these experiments, we measured the heat release rate due to burning. I don't want to intimidate anyone with over-technical language or data, but I do think it's important for transparency, if nothing else, for me to show you the kinds of data that I've considered in performing my analyses and drawing my conclusions. So this slide shows the measured heat release rate that was recorded during the experiment that I've just shown you. You can see that we recorded negligible heat release up until the point of ignition of the Renabond PE, at which point the heat release rate increased rapidly to a peak value before then decreasing again as the sample ran out of polyethylene fuel. And you can also see how quickly that happened. If we calculate the area underneath this heat release rate curve, we can obtain an estimate of the total amount of energy that was liberated as that sample burned. Similar plots were developed and compared for all of the Work Package 1 experiments that we performed. During our experiments, we also, as I've mentioned, continuously monitored the amount of mass lost from the experimental sample and the amount of mass gained by the debris tray that was situated below the sample. These data are shown here, mass lost on the left-hand side and mass gained on the right-hand side. And by comparing the mass of the sample with the visual observations, we observed a sudden decrease in the sample mass at 1 minute and 22 seconds, and this occurred when the front plate of aluminium fell from the specimen. The recorded decrease of sample mass corresponds with the expected mass of the aluminium facer plate. There's a corresponding increase in the mass of the debris tray at the same moment that you can see, and there's a gradual sample mass loss that follows this loss of the aluminium plate, and that's associated with both burning and dripping of the polyethylene core material. During this period, the debris tray gains mass due to dripping. However, all of the mass lost from the sample is not gained by the debris tray, and clearly this is because some of the polyethylene has been consumed by burning before it reaches the debris tray. Similar plots, again, were developed and compared for all Work Package 1 experiments. Now, I don't have time to rehearse all of our results from all of our experiments, many dozens of experiments. So I'll simply summarize what I found in the next few moments. Of the 4 cladding products considered in Work Package 1, Renabond PE has the largest potential to contribute to fire growth and spread. It accounted for as much as 59% of the total potentially available energy on any single floor of Grenfell Tower, and as much as 87% of the total potentially available energy within the architectural crown. Of the 4 principal cladding products, Renabond PE is comparatively slow to ignite. However, once ignited, it releases more energy more quickly than any of the other products. In my Work Package 1 report, I conclude that Renabond PE was the largest contributor to energy release in the cladding at Grenfell Tower. I found that the time to ignition of Renabond PE is not strongly influenced by the manner in which the panels are fixed, i.e. riveted or routed in a cassette format. However, the subsequent rate of burning is likely to be influenced by the fixings, by which I mean a riveted versus a cassette configuration, with riveted systems likely to perform better in general. I also found that the balance between burning of the polyethylene core material in situ, i.e. at the location of the sample, and its mobilization downward by dripping whilst burning is significantly influenced by the method of forming and fixing. I've concluded that in most cases, the majority of the polyethylene core material is likely to have mobilized downward during heating. This is likely to have been accompanied by flaming of the downwardly mobile material and the formation of pool fires where it was able to collect on horizontal surfaces, both within and outside the rain screen cladding system. This corroborates my observations regarding fire spread mechanisms from the fire at Grenfell Tower that I made in my Phase 1 evidence to the inquiry. I've shown that Renabond PE, when locally heated directly on an exposed cut edge, which I've not shown you the results of, fails to ignite or spread flame at heat fluxes up to 75 kilowatts per square meter. This was the most severe heating exposure that I used in my experiments, and suggests that edge ignition under very localized heating is unlikely under most circumstances. one needs to more uniformly heat Renabond PE over a more substantial area in order for fire growth and spread to occur. I performed similar experiments on the foil-faced thermosetting polymer foam insulation products used within the external wall arrangement at Grenfell Tower, namely the Celotex RS5000 and the Kingspan Cooltherm K15. I knew that these insulation products, without their foil facers in place, would be relatively easy to ignite due to their low thermal inertia. I knew that both products are charring thermoset polymer foams, and I therefore expected that they would ignite quickly and experience a rapid rise in heat release up to a peak value, but that they would then experience reductions in heat release rate and may even extinguish or go out in the absence of a significant external heat flux because of their charring nature. I knew that the foil facers on both products would drastically alter the heat transfer at their surfaces, would interfere with ignition, and would significantly complicate and improve their initial burning behavior. I'll now show you some videos of my experiments on the insulation products. I'll show you two on Celotex RS5000 at a heat flux of 50 kilowatts per square meter, as for the ACM a few moments ago, both with and without a foil facer in place, and two on Kingspan Cooltherm K15, also at a heat flux of 50 kilowatts per square meter, and again, both with and without the foil facer in place. These videos clearly demonstrate the criticality of the foil facer as regards ignition and burning for these products. I'd just like to reissue my trigger warning, as we'll again be watching videos of products that burned at Grenfell Tower. So this slide shows two different experiments on Celotex RS5000. This is the RS5080 product, both with and without the foil facer in place, obviously without the facer on the left. Again, the samples are being heated from the right-hand side, so the radiant panels are shining onto the rightmost face on these samples. Before I press play, I'd like to warn you to try and notice the speed with which the RS5000 insulation ignites when the foil facer isn't present. If you blink, you might miss it. After ignition, we'll see that there's no obvious melting or dripping from the sample, which is why I'm not showing the debris tray in these experiments. Nothing falls down. I'll explain now what we're going to see. We will observe the formation of a layer of char over the surface of the sample on the left-hand side. This will result in a gradual reduction of the flow of flammable pyrolysis gases through the front face of the sample, and this will result in a reduction of the severity of burning, and eventually the flame will become intermittent on the surface and may even go out briefly. We'll see the char will then crack, allowing flammable gases from deeper within the sample to exit the front face, and flaming will then persist for several minutes before again extinguishing. On the right, with the foil facer present, we'll not see any ignition at all for the full duration of the experiment. I'd like to remind you that the foil facer on this product is only about 30 microns thick. That's 31 thousandths of a millimeter thick. And yet, its influence on the reaction to fire behavior is profound. We will see the formation of bubbles behind the foil facer. This is an indication of the generation of pyrolysis products being generated from the PIR foam behind the foil, and those pyrolysis products are unable to escape, thus preventing their mixing with oxygen and their burning. So I'll now let it run, again, stopping periodically. So you can see ignition at time 0 in this case, which is the moment that the radiant panels actually come to a rest in front of the sample. So they ignite essentially instantaneously. After ignition, there's no obvious melting or dripping, again, because these are thermosetting polymers. We see continuous flaming and the formation of a char layer over the surface of the left-hand sample. This results in a gradual reduction of the severity of burning as we watch it play forward. On the right, in a moment, we should see the formation of bubbles in the foil facer. So there you can just make out the formation of a bubble in the foil facer. On the left, we'll see the flaming reduce and become intermittent. So there we see the intermittent flaming, and this continues until the char cracks, at which point we see the flaming increase a little bit more. So there you can start to see the formation of a crack in the front face of the char in the left-hand video. So there's cracks formed in the char surface, and flaming then persists for several minutes. Now I'm going to let the video run at 40 times the normal speed, because these are 20-minute long tests. And we can see that the sample, which is protected by a foil facer, doesn't ignite at all during the course of an otherwise identical experiment, whereas the unprotected sample is gradually consumed as it runs forward. So now I'll show you the same comparison for Kingspan Cooltherm K15 insulation, and you'll notice some differences in behavior. Again, a trigger warning. I'll show two videos of experiments on Kingspan Cooltherm K15 insulation at the same heat flux, 50 kilowatts per square meter, both with and without the foil facer in place. In this case, on the left, we will see that ignition doesn't occur as rapidly as was the case for the Celotex RS5000, taking about 16 seconds for the sample without a foil facer. After ignition, we'll see that there is no obvious melting or dripping from the sample, as was the case for the RS5000. And again, this is because phenolic foam, like PIR foam, is a charring thermoset polymer. We'll observe the formation of a char layer over the surface of the sample, which will again result in a reduction in the flow of flammable gases through the front face of the sample. This will again result in a reduction of the severity of burning, and eventually, in this case, extinguishment of the flame completely. However, we'll then observe that the char will begin to glow, and that the sample will gradually be consumed by a combination of smoldering combustion and physical loss of material from the foam's surface. On the right, for the sample which is protected by a foil facer, which in this case is only about 25 microns thick, so 25 1,000ths of a millimeter, again, we won't see any ignition. We'll also notice that we won't see any bubbles forming in the foil facer for the K15 product. This is obviously because the foil facer is perforated, and the flammable gases can easily get out of the sample, so to speak. So now I'll let it run. So there we have ignition at about 16 seconds. Beyond ignition, there's no obvious melting or dripping from the sample, as I've mentioned. We can see the formation of a char layer over the surface of the sample and a reduction of flaming. Quite rapidly in this case, we get a reduction in flaming. The char then begins to glow, and the sample is gradually consumed by smoldering and a physical loss of material from the foam's surface. And once this has stopped and I've pointed to the glowing, I'll let the experiment run at 40 times its normal speed. So you remember that the RS5000 did not glow like this. The K15 sample, which is protected by a foil facer on the right, does not ignite. The sample without the foil is gradually consumed and continues to smolder throughout this experiment. And this behavior was fairly typical for the Kingspan product. Again, I don't have time to rehearse all of the results from my experiments on both of these materials here. So in a moment, I'll just summarize what I've observed and concluded. And you can see at the end of this experiment, there was actually not that much material left on the left-hand side. And of course, we could quantify the amounts of material consumed because these samples are on scales, and we know how much mass is being lost throughout these experiments. So now to some results. The PIR foam core of RS5000 and the phenolic foam core of K15 have lower heats of combustion than the polyethylene core from Renabond PE. Of the 4 principal cladding products at Grenfell Tower, assuming that the vast majority of the insulation installed was RS5000 rather than K15, RS5000 would make the second highest contribution of available energy per floor. I found that with their aluminium facers in place, RS5000 and K15 are both comparatively difficult to ignite. However, I found that when the foil facer was present on both products, Kingspan K15 was easier to ignite than the Celotex RS5000. And as I've already noted, I consider that this is due to the presence of the perforations in the facer. I found that without their foil facers, both insulation products are very easily ignited. This is a consequence of their very low thermal inertia, and indeed is precisely why these products are otherwise so very attractive for providing thermal insulation in buildings. Once ignited, sustained exposure to heat fluxes between 25 and 75 kilowatts per meter squared resulted in gradual thermal decomposition of both types of polymer foam core, and this was accompanied by charring and comparatively low heat release rates if you compare to the ACM PE. Also, the time scales over which this heat release occurred for the polymer foams is longer than those of external fire spread when a Renabond PE ACM product is used, by which I mean the ACM would have burned away long before we would have observed these mass losses. Once ignited, both insulation products have much lower heat release rates per unit area than Renabond PE. Once ignited, neither of these products melts or drips, although the Kingspan K15 does have a tendency to both lose section and smolder under sustained heating. It appears that flat samples of either of these products tested in isolation do not spread flame horizontally in the absence of an applied external heat flux. Neither of these products are therefore considered to have been primary or decisive contributors to heat release during the Grenfell Tower fire, particularly within the timescales relevant to vertical fire spread up. I'll talk more on this last point in presenting my work package 2 experiments later this afternoon, which is really focused on trying to really unpick that question. So that concludes the summary comments I wanted to make regarding my work package 1 experiments. There is, however, a lot more information contained within my work package 1 report, and obviously I'd encourage all interested parties to have a look at this. Next, I'll move on to discuss my work package 2 experiments. However, looking at the clock, I wonder if it might be a good time for a break.
I think it probably would, wouldn't it, before we start your next section. So we'll take the break now slightly earlier than we usually do. We'll resume, please, at 3:25. And in common with all the other witnesses, I have to ask you not to discuss your evidence while you're out of the room. Yes, thank you. 3:25, please.
Thank you.
Thank you. Thank you, Mr. Millett. 3:25, please. Thank you. Would you ask Professor Bisby to come back in, please? Yeah. Right, Professor Bisby. Well, when you're ready, we're ready for you.
Thank you.
Thank you.
Thank you, Mr. Chairman. So before the break, I discussed how the cladding products of primary interest responded to heating conditions that are representative of cladding fire scenarios. The heating scenarios that I used in my Work Package 1 experiments are most relevant to situations where you already have a big fire. For instance, a fire plume generated by a fully developed fire within a building compartment venting out of a window. I illustrated some of the key burning behaviors of the main cladding products that were present at Grenfell Tower. I also intimated that the mechanical responses of the products could also affect their burning behavior, even when burning in isolation. However, those previous experiments, the Work Package 1 experiments, by themselves, don't help us to fully understand how these products might have interacted within the external wall arrangement at Grenfell Tower. Notwithstanding a host of complexities, including the presence of various other materials and products, cavity barriers, etc., as convincingly demonstrated by Professor Torero this morning, the ventilated rain screen cladding system at Grenfell Tower was, in essence, a single outer surface and two surfaces facing one another across a ventilated cavity. Again, as shown here in the highlighted area. The development of fires in configurations like this is complicated because of the complex combustion environment within a ventilated cavity and because there are interactions between the surfaces on either side. There is thermal feedback between the surfaces. If one surface gets hot, then this will heat the opposing surface, and so on. There is also flow within the cavity, and the question of how the energy released by burning is distributed within the cavity. Is heat lost out of the top of the cavity? Is heat retained and fed back to materials and products within the cavity, thus promoting fire spread? My Work Package 2 experiments were focused on this type of ventilated cavity configuration of products. Again, the time available to me will not allow me to cover all of the material contained within my Work Package 2 report. So in the interests of time, I'll be blunt about the fundamental questions that I, again, working with my team at the University of Edinburgh, and again in close consultation with Professor Torero, set out to answer in Work Package 2. Did the Renabond PE ACM burn so vigorously simply because of the presence of a cavity at Grenfell Tower? Or did the Renabond PE ACM burn so vigorously because it was very well insulated by the other products at Grenfell Tower? Or did the Renabond PE ACM burn so vigorously because of additional burning of the combustible Celotex or Kingspan insulation products at Grenfell Tower? To try to provide answers to these questions, I needed to design another bespoke experimental apparatus. The apparatus had to deliver consistent and repeatable results, and it had to allow systematic exploration of the relative contributions of the different products. The complexity and variety of real cladding geometry at Grenfell Tower would make systematic study of all possible permutations that existed on the building impractical. My objective was not to make a reconstruction of Grenfell Tower or to rate the products or systems, but to study the physics that might be relevant to fire spread at the tower. I wanted to understand rather than to rate or reconstruct, and it's very important that I make that distinction. We decided, therefore, to create an experimental apparatus that featured two parallel surfaces with a ventilated cavity in between them, parallel plates, if you will. We selected a geometry that we felt was relevant, similar to the horizontal panel joint between rain screen cassettes of Renabond PE on the columns at Grenfell Tower. However, again, I must stress this is not a reconstruction. On one side, I placed a panel of Renabond PE ACM rain screen, and on the other side, I placed a panel typically of insulation. I used a propane gas burner as an ignition source. This was essentially a metal pipe with small holes in it. The propane supply to the burner was carefully controlled using a mass flow controller, and this meant that I could control precisely and maintain precisely the size of the flame both within and between experiments. I placed this propane burner on a slider that allowed me to move it into and out of the rain screen joint, as I've shown in this diagram. I recognized, as I've already said, that melting, mobilization, and pooling of the polyethylene from the ACM rain screen would have a significant impact on fire development. I therefore knew that controlling the consistency of pooling of the polyethylene would be important in achieving the experimental repeatability that was essential if I wanted to isolate and study the influence of other experimental parameters. I placed a small drip tray, shown here, on the ledge under the burner. This would allow me to collect dripping polyethylene in a consistent way between each of the experiments and to ensure experimental repeatability. Because I was interested in these experiments in escalation of the fire upwards, the lower part of the rain screen was fabricated in solid steel, that's the steel shelf shown here, rather than in ACM. And I constructed a series of supporting frames to hold this arrangement in place with open sides so that I could see or look into the cavity as the experiments progressed. So from the side, the overall setup looks like this. And again, I'll show you with some photos in a moment that should make it a bit more clear. And from the front, which is perhaps even less clear as a drawing, it looked like this. You can see that the panel of ACM in these experiments was about half a meter wide, 500 millimeters, by about 1 meter tall, about half the size of me if I were to stand facing you. The apparatus was assembled as follows, so I'll show you how it's built up. First, we have 2 load cells. These are very precise digital scales. We have aluminium frames that sit on top of the load cells, one to hold the ACM rain screen and one to hold the opposing face of the cavity, which was typically, but not always, as we'll see, a sheet of polymer foam insulation. 2 more load cells that sit above the initial 2 load cells so that I could weigh both the samples and any falling debris independently of one another as the experiments progressed. Metal trays to catch any debris, again, one for the ACM and another for the insulation or whatever was on the opposing face of the cavity. The components of the specific experiment being performed, in this case, I'm showing a Renabond PE ACM rain screen and an opposing face consisting of foil-faced Kingspan Cooltherm K15 insulation, and you can see there's a cavity between the two of about 100 millimeters in these experiments. A velocity probe to measure the airflow velocity at the midpoint of the cavity, and a variable number of thermocouples to measure temperatures at various locations on the ACM and within the insulation. Here you can also see the propane line burner on the left, mounted on a chassis that sits upon a slider so that I could move it into and out of the joint below the ACM. And you'll see how this all plays out in a moment. This photo shows the line burner in a standby position, and this photo shows the line burner in position within the rain screen joint. I'll just go backwards and forwards a couple of times so you can see how it moves. Overall, the apparatus looked something like this. And here you can see that we also used a large number of cameras to capture simultaneous videos from various vantage points during the experiments, and I'll show you some of these videos in a moment. Before I do that, however, I just want to show you how we cut and formed the Renabond PE panels for our experiments, because this is actually very important. This slide shows the rear face of a Renabond PE ACM panel mounted on its aluminum supporting frame before an experiment was conducted. You can see that we have cut the edges of the panel and left the black polyethylene core exposed along the panel edges. You can also see that we have routed the surface of the panel that faces into the cavity. So you're looking at the surface of the ACM that would face into the cavity, looking at the opposing face. And we've done this so as to fold it to create the horizontal ledge that you can see at its base. We've also routed vertical lines down the sides of the ACM panels so as to create free-floating, if you will, plates of aluminium which are attached to the sample only via the ACM's polyethylene core. Otherwise, the bolts that you can see down the side of the sample would have held that inside face in place. And this is akin to the condition that would exist on the inside face of an ACM range screen cassette, which is obviously why we've done it, such as those used at Grenfell Tower. Rather than explain every experiment in detail, again, I'll show you just one example experiment, and I'll then focus the rest of my presentation on what I've found to the extent that I have time to cover it, and what I've concluded. Again, I've made videos of all of my experiments available via the inquiry, and have also produced a number of composite comparative videos that are available within and referenced within my Work Package 2 report. The example experiment I'll show you in detail, which was selected essentially at random, was on Renabond PE ACM and Kingspan Cooltherm K15 insulation with the foil facers intact. This is experiment number 21 in my Work Package 2 report. Before showing you the video, I'd like to walk you through the heat release rate data that we recorded during this experiment. This helps to place key moments that I'll highlight within the video within the context of the fire sizes and the fire hazards that resulted. This graph shows the heat release rate, HRR, that we measured from the beginning of experiment 21, starting at time 0, essentially on the left, to the end of the experiment after 20 minutes. And we ran all of these experiments for 20 minutes. Unless, of course, they ended much sooner than that, or unless we had to stop for health and safety reasons. The HRR on the vertical axis is effectively telling us the size of the fire in terms of the amount of energy it's releasing at any given moment in time. So the higher that line, the more energetic the fire is. At time 0, you will see that the line burner is introduced into the cladding joint within the experimental rig, and I'll show you a video of this in a moment. You'll then see that the polyethylene core from the ACM begins to melt and to drip into the drip tray beneath the ACM panel joint. After 4 minutes, you'll see that the line burner is removed, but that there is a small pool fire of burning polyethylene within the drip tray. You'll also notice that we leave the line burner burning. It's a bit distracting in the leftmost view that you'll see. There's a line burner there throughout, but it's pulled away from the sample in that condition. The fire will then steadily grow during the course of about 6 minutes, and we'll then observe a jet of flames from the top of the Renabond PE range screen from about 10 minutes into this particular experiment. Shortly after this, we'll observe, if we look very closely, separation of the inside aluminium skin of the Renabond PE, resulting in a very rapid and violent escalation of burning. And this is what I refer to as escalation to full involvement of the ACM in my Work Package 2 report. It then increases to a peak heat release rate value. The polyethylene from the Renabond PE gradually burns away over the course of a few minutes, and the foil-faced Kingspan Cooltherm K15 continues to smolder and flame, in this case until the experiment is terminated after 20 minutes. Again, a trigger warning is warranted here. This video I personally find particularly shocking. Okay, so this image shows 3 different views of our experimental arrangement. Camera A is from the front. You're basically looking at the outside face of the Renabond PE. This would be equivalent to standing outside the building and looking at its external surface. You can see the propane line burner in the foreground. It's in its standby position here. It has not yet been inserted into the range screen panel joint in the test assembly. Camera B, which is a bit dark admittedly in this view, shows the apparatus from the side. You can see the cut edge of the pink K15 insulation at the right-hand side of the camera B view. And camera C, also from the side, but in this case it's a close-up of the location where the burner is inserted into the panel joint. And again, you can see the insulation on the right-hand side. And you can see that the foil facer, if you look closely, is still there in this case. The experiments commence when the line burner moves into the ACM rain screen joint. The burner is then held in place, as I've mentioned, for 4 minutes before being removed and allowing the fire to progress, or not, under its own steam. I'll now talk through the video of this particular experiment and highlight, as I've been doing previously for the other videos, the various points of interest. The experiment begins by moving the burner into the joint in the ACM. You can see that when the burner is moved into the joint, the flame is drawn into the cavity and begins to interact with the ACM. Again, I'm showing this at 10 times speed. It takes around 1 minute and 30 seconds of heating before the polyethylene starts to drip out of the ACM and into the tray below. You can view that particularly in the leftmost view here. For about 90 seconds, the rate of dripping increases. Now, it's quite hard to see in this next video, but at 3 minutes and 12 seconds, there's a free-floating aluminium plate on the upper side of the aluminium ledge at the base of the ACM, and it drops into the drip tray. It's going to be in this view over here. If you remember back to the photo I showed of the routing of the aluminium composite material, the aluminium plate along the top of that shelf is essentially free-floating on a layer of polyethylene, and when that polyethylene melts, the plate drops off. We've intentionally angled that shelf down at 5 degrees because we found that we needed to do that in order to ensure consistency amongst the tests. So we tried to make it so that that plate would consistently fall off, if you will, which gives you a sense of the complexity of the response of these systems. So just there, the plate dropped off. Up to about 4 minutes, a pool fire of burning polyethylene continues to grow within the drip tray. The flames extend to about 3/4 of the cavity height by about 4 minutes. And remember, this entire rig is about 1 meter high, that sheet of ACM PE. At 4 minutes, the line burner is removed. And after 4 minutes, the flame height within the cavity continues to increase gradually as more molten PE mobilizes and exits the ACM panel. At about 5 minutes and 19 seconds, we'll see that the flames become visible above the experimental apparatus, and you'll see this particularly in the leftmost view. And you remember now that the line burner has been removed, so this is just burning polyethylene. So you can see in the leftmost view, flames above the rig. Between 6 minutes and 30 seconds and 8 minutes and 50 seconds, the inside vertical aluminium face of the ACM begins to separate from the polyethylene core material, and you'll start to see that over here in this rightmost view. That line there is showing the routing line along the ACM PE. Flames become visible on the inside of the ACM, and the flames overall will now extend well above the apparatus. At 9 minutes and 9 seconds, if you watch the highlighted area at the top of this slide that I'll show you in a moment, you'll see that flaming becomes visible on the surface of the foil-faced K15 insulation. So if you watch that highlighted circle, near the end of this clip, you'll see some flaming of the insulation. It's a bit clearer in a moment. The flaming then continues at this location, albeit only briefly. Now, I've previously noted the potential significance of the perforations in the foil facer for the K15 product in particular, and this allows the flammable pyrolysis products to exit the insulation directly and enter the cavity whilst the facer is still in place. At 10 minutes, flames can be observed in the top leftmost picture. It's easier to see once I let it run again, but you can observe that flames are now exiting the top of the ACM panel itself. and that'll be shown at the top left. This will persist until about 10 minutes and 32 seconds, when it appears that the entire inside face of the aluminium sheet facing into the cavity separates from the ACM, thus fully exposing the remaining polyethylene core material. And after this point, we observe this violent escalation to full involvement of the ACM, and I'm going to simply let this portion of the video play. And again, apologies, the graphics card I think is having a hard time keeping up with these videos. Even having witnessed this escalation in person now dozens of times, I still find it pretty shocking. Indeed, the comparatively small size of our experiments, in general terms, was dictated by the fact that these were the largest experiments that we felt we could safely perform within our purpose-built fire labs. These were some of the most shocking experiments I have ever witnessed after about 15 years of working in these labs. And I feel at this point that I should remind you that this is the experimental arrangement burning without any external stimulus. The line burner has long since been removed. This continues until about 13 minutes and 30 seconds, and after this point, we will be looking essentially directly at the K15 insulation through the Renabond PE, or where the Renabond PE used to be. The last visually obvious flaming from the polyethylene from the ACM occurs at around 18 minutes when I let this run. The Kingspan K15 continues to smolder and flame until the experiment is terminated after about 20 minutes. So, just to return to the heat release curve that I showed before we viewed the video, this slide just recaps those observations. Insertion of the line burner at 0 minutes, first drips of PE at about 1.5 minutes. Aluminium plate on the top of the ACM PE shelf falls into the drip tray before the line burner is removed. The line burner is then removed after 4 minutes. The fire then grows gradually over a few minutes. There's some apparent partial separation near the base of the ACM as that fire is growing. We then see visible flaming within the ACM, i.e. between the two aluminium skins of the ACM near its base. We see loss of insulation foil facer just prior to escalation. We then see a jet of flames that appears to be coming out of the top of the ACM itself from between the two aluminium plates, separation of the inside aluminium skin, very rapid and violent escalation up to the peak heat release rate, and then a slow decay over a period of a few minutes until the PE stops burning and we finish the test after 20 minutes. Now, as I've said, I don't have time to go through all of our experiments. That just gives you a flavor of the kind of things we observed and the way in which we tried to go through each experiment very carefully and to pick out why we had observed what we had observed, to understand the physical underpinning mechanisms for what we were observing in our data, which is really important. And so that going through the heat release rates curve, looking at the changes in behavior, going back to the videos and trying to articulate in physical terms or in heat transfer terms why what we were observing was happening. And in the end, we undertook 37 experiments on basically this overall general arrangement, varying parameters of interest, so as to try to answer the 3 questions that I posed near the beginning of this presentation, this section of the presentation. So I'll now take you through my findings. And for transparency, I should say that the order in which I'm going to present my findings is not the order in which we performed the experiments. I'm presenting the results in the order that I believe will be the easiest to explain and hopefully to understand. So just to remind you, my key questions were, essentially, was it the cavity? I.e., was it the fact that we had the geometry of a cavity? Was it the insulation? I.e., the fact that the opposing face of the cavity was insulating, keeping energy within the cavity? Or was it the combustibility of the insulation? The fact that the opposing face of the cavity could burn, thus contributing more energy to the system. To better understand the role of the cavity, specifically, first we did what seemed logical and we performed an experiment without any cavity. In this case, an experiment only with the Renabont PE panel, configured and ignited identically to the other experiments that involved cavities. So everything identical to what I've just shown you, but with only a sheet of ACM PE. No cavity, no insulation. And I'm just going to show this for you in the interest of time at 10 times speed. So you can see the burner gets inserted. After about 1.5 minutes, you see dripping. We see the aluminium plate fall off of the little shelf on the ACM PE. We will see the line burner removed at 4 minutes. And we will see that eventually this experiment goes out. So we do not observe escalation to full involvement of the ACM in this case. And eventually what you would see is that small polyethylene pool fire gradually just burns itself out. You'll have to, perhaps in the interest of time, maybe take my word for it. So this experiment with no cavity showed that if no insulation products were present to form the geometry of a cavity, then escalation did not occur. However, I was uncertain. Was this because the geometry of the cavity was absent, or was it because the product from which I had formed a cavity, for example, the K15 insulation board in my experiment 21 that I showed you, was highly insulating, or because it was combustible? To answer this question, we created a non-insulating cavity using Renabont PE on one side and a continuously water-cooled steel plate on the other, essentially a steel plate with a cascade of water running down its rear surface. The steel plate stayed at low temperature throughout the experiment and actually represented a heat sink that would remove energy from the system during the experiment. So it creates the geometry of a ventilated rain screen cladding system, but without insulating it at all, in fact, taking energy away from it. Again, we found that escalation didn't occur. This meant that the presence of the cavity alone was not sufficient to cause escalation using our specific experimental configuration and procedure. I consider this to be a really interesting result. The geometry of the cavity and the resulting flow conditions within the void by themselves did not lead to escalation of burning of the Renabont PE. To induce an escalation, I needed the insulation product to either insulate the ACM, thereby retaining energy within the system, or to burn, thereby contributing energy to the system. I'll first discuss what happens when I used a non-combustible but insulating product. Note that the product that I used, which was a mineral wool product, is deemed to be non-combustible from a regulatory perspective, i.e. it is a Euroclass A1 product. It does not, however, actually have a heat of combustion of 0, which would make it actually non-combustible. And I think that's an important distinction to make at this point. When this non-combustible insulation product was used, I found that escalation occurred. That is, the Renabond PE became fully involved in the fire. I consider this to be a very interesting result. It suggests that the insulation product did not need to burn in order for an escalation to occur. It was sufficient that the insulation product allowed heat to be retained within the system. Having established that escalation could occur in the absence of a combustible insulation product, the next question is therefore, if the insulation product is in fact combustible, does it make matters worse? By which I mean faster or more energetic. And if so, by how much? So I undertook additional experiments with combustible insulation. I removed the foil facers from Celotex RS5000 in an attempt to maximize the possibility of an energy contribution from the PIR foam to the fire. And in this experiment, I also observed escalation. From analyzing the data, I concluded that this occurred slightly earlier than for the equivalent case with non-combustible mineral wool insulation. This may be because of an energy contribution to the system from the combustion of pyrolysis products coming from the insulation itself. The insulation did ignite rapidly and did spread flame over its surface in this configuration. It may also be because the thermal inertia of the PIR foam core from RS5000 is considerably less than that of the mineral wool insulation I had used, i.e. it's a better insulator. Probably both factors are relevant. I then undertook similar experiments, this time with Kingspan's K15 phenolic foam insulation product. Again, I removed the foil facing from the insulation. And again, I found that the results were very similar to the case of PIR with no foil facer. Escalation occurred, and again, it occurred more quickly than for the non-combustible insulation case. I observed that the K15 continued to smolder for some time after escalation, and in some cases continued flaming for quite some time. The Celotex PIR foam did not display this behavior. The fact that these polymer foam insulating products were combustible thus appeared to be of relatively little importance, compared to the fact that all of these insulation products, whether combustible or not, were very effective at retaining heat within the cladding system. The insulating nature of these products, rather than necessarily their combustibility, resulted in more rapid and widespread heating of the Renabond PE, more rapid mobilization of a larger volume of polyethylene core material, more rapid separation of the inside aluminium skin over a larger area, and therefore more rapid escalation to full involvement of the Renabond PE in the fire. The fact that the polymer foam insulation products could burn appeared to be of secondary importance, as compared to their insulative properties. At this point, I'd like to return again to the original questions that I posed at the beginning of this presentation. Did the Renabond PE ACM burn so vigorously because of the presence of a cavity at Grenfell Tower? Based on these experiments, I would suggest that the answer to this question is no. The cavity by itself did not cause the Renabond PE to burn so vigorously. Did the Renabond PE burn so vigorously because it was very well insulated by the other products at Grenfell Tower? Based on these experiments, I would suggest that the answer to this question is yes. To answer the last question, did the Renabond PE ACM burn so vigorously because of the additional burning of the insulation products at Grenfell Tower? I wanted to perform some additional experiments using the combustible insulation products. I also wanted to better understand the role of the aluminium foil facers, given that one would hope that these would typically actually be present in practice in one of these systems. Now, if you recall, in the experiments that I've discussed thus far, I chose to remove the foil facers from the insulation products. Of course, we know that while there were exposed edges of insulation within the cladding system at Grenfell Tower, most of the insulation products, whether RS5000 or K15, had foil facers in place. In the case of the Kingspan product, again, the foil facer is perforated. I therefore repeated the above experiments, but in each case I retained the foil. I therefore repeated the above experiments, but in each case I retained the foil on the front face of the insulation, including having foil on the front face of the combustible mineral wool insulation. For the mineral wool insulation, I found that the presence of a foil facer caused escalation to happen more rapidly when compared with the no foil case. Possible reasons for this, which are quite complex, are discussed, and they're slightly counterintuitive, it has to be said. They're discussed within my Work Package 2 report, but I don't want to go into it here. For both the RS5000 and the K15, however, I found that the presence of the foil facers caused escalation to happen less rapidly when compared with the no foil cases. This is probably unsurprising, given that the foil slows the production and restricts the flow of flammable pyrolysis products from the polymer foams themselves. I analyzed the heat released by all of these insulation products from the start of each experiment until the time at which the escalation of the fire occurred, and I found that the contribution to the total heat released from the combustible insulations with foil facers up to the point of escalation was measurable but minor. In the cases of combustible insulations without foil facers, I found that the contribution to heat release up to the critical time, i.e. the point of escalation, may be comparable to that of the ACM itself. I consider this to be a useful summary slide in some respects that gives an overview of the differences between the various configurations that I've investigated in my Phase 2 Work Package 2 experiments. This plot shows the total amount of energy released during different experiments, so each bar represents a different experiment, the total amount of energy released during different experiments on different combinations of products, with each experiment performed twice, which is why you have 2 of each bar. We ran every test in duplicate because we wanted to check the repeatability of our results. You can see that all cases that involve insulation of the cavity are broadly similar, whether the insulation was combustible or not, and whether foil facers were present or not. So for the RS5080, the 5100, the K15, and the mineral wool, with and without foil, you end up with a total heat release that is broadly similar. The highlighted bars here show the total amount of energy released during experiments involving Renabond PE with Celotex RS5080, the 80 millimeter thick variant of RS5000. You can see there are 2 experiments that involve foil facers. Those are the dark bars, the 2 dark bars, and 2 experiments that have, without foil facers, and those are the lighter bars. Despite the earlier escalation to full involvement of the Renabond PE when the foil facers were removed, that I just mentioned, these data suggest, in this plot, very little difference in the total amount of energy released up until local burnout of the cladding system, i.e. during the 20 minutes of the experiments that we performed. The same is true, in broad terms, for the Celotex RS5100 product, the 100 millimeter thick Celotex product, and for the Kingspan Cooltherm K15, although in this case there does appear to be slightly more heat release in general. This is likely a result of the ongoing smoldering and flaming that I commented on when we looked at that experiment a few minutes ago. And much the same result for the mineral wool insulation, although in this case there is slightly less total heat release. So you can see those bars are all slightly lower than we get for the polymer foam insulations, probably because this insulation contains very little fuel to release in the first place. You can also see that whilst the presence of the foil facer might slightly change the time it takes for escalation to occur, it does not drastically influence the total amount of energy that is eventually released for any of the insulation products. This is yet another indication of the dominance of the Renabond PE ACM to this fire. Finally, in cases where there was no escalation, i.e. where the cavity was not insulated at all, there was, or there was no cavity at all, the total heat released was very small, albeit there does appear to be a small influence from the presence of the cavity. The experiments that had cavities, if you watch the videos, you'll see that the pool fire is larger and burns for longer in those cases, hence a slightly higher heat release. Now this brings me to the end of my main comments on my work package 2 experiments. There were other experiments and other questions, but I'll not rehearse these today as they're documented in great detail in my work package 2 report. Instead, I'll simply emphasize my conclusions. In all of my evidence to the inquiry to date, I have consistently identified Renabond PE as the primary cause of rapid fire growth and spread during the Grenfell Tower fire. My experiments have allowed me to quantify the relative contributions of the main cladding products to the rate and extent of fire growth and spread. My experiments have highlighted the immense complexity of the heat transfer environment within a ventilated rain screen cladding system, even for the relatively small and simple cladding system arrangements that I've tested. This suggests, to me, that an intuitive understanding of the factors that govern fire initiation, growth, and spread in such systems can very easily lead to incorrect assumptions, as Professor Torero intimated as well this morning. It remains my view that of the products and materials present in the external wall assembly of Grenfell Tower, the Renabond PE was primarily responsible for the rate and extent of fire spread. With respect to the role of the insulation products, I have found that it was primarily the thermal properties of the insulation products which caused the Renabond PE to burn so vigorously. The fact that these products are exceptionally good insulators made matters much worse for the combustible rain screen that was used. I found that the combustibility of the insulation played an obvious role only when large surfaces were unprotected by foil facers, and only insofar as it accelerated escalation to full involvement of the Renabond PE. Thus, the combustibility of foil-faced insulation foams at Grenfell Tower appears to have played only a minor role in causing the polyethylene to burn so vigorously. Whilst I've not discussed the results in my presentation today, my experiments have also highlighted the importance of the mechanical fixing details of the ACM rain screen panels and their manner of routing, folding, and riveted on the fire growth and spread in ventilated rain screen systems incorporating these cladding products. Finally, it's noteworthy that I've not considered any smoke production issues as part of my investigations at all. Questions around toxicity and smoke production are relevant, but are being addressed by other experts to the inquiry. Given the context of this work and the evidence heard by the inquiry thus far, I'd like to make a few general closing remarks, if I could. First, it's clear that Renabond PE ACM presents extreme fire hazards. It is a very, very burny material. Indeed, all ACM PE products present extreme fire hazards. There are few construction products intended for any use on the outside of a building that I have ever seen burn with such intensity. Every time we ran an experiment that escalated to full involvement of the ACM, I was surprised and alarmed. Once you've seen how these products behave under realistic fire exposures, if you know anything about fire safety and anything about the testing methods that were being used to classify reaction to fire performance of cladding products in England, you must surely know that these products are uniquely hazardous. What you, as a regulator, a designer, or an approver, then do with this knowledge is up to you. Second, given the conclusions resulting from my work package 2 experiments in particular, I want to emphasize that just because the physics tells us that a particular material or product may or may not have governed what occurred at Grenfell Tower, this does not, in my view, mean that the inquiry shouldn't seek to understand as fully and completely as possible how these products came to be installed within Grenfell Tower, in the external wall arrangement, or the culture and context within which this occurred. I want to finish my pre-prepared evidence by thanking the chairman, the panel, and the wider inquiry team for allowing me and my team the freedom, tremendous freedom actually, it has to be said, to undertake our phase 2 experiments as we saw fit. Thank you very much.
Well, thank you very much, Professor Bisby. It's been a fascinating afternoon. And we're very grateful to you for conducting so many experiments with such care and for recording them in a way that enables us to understand what you've done.
I should say again, full credit to the team, the wider team at Edinburgh, for that work.
Of course, yes. Thank you very much. Yes, Mr. Millett.
Well, that concludes Professor Bisby's presentation, for which we're all extremely grateful. Thank you, Professor. And we will invite the Professor to return on Monday morning for some questions.
Yes. Well, we look forward to seeing you again on Monday at 10 o'clock, and we'll see what questions there are for you.
Thank you.
Thank you very much indeed. Thank you very much, Mr. Millett. Well, that's it for the day.
It is, yes, Mr. Chairman. Thank
you. And as I just indicated, we'll resume at 10 o'clock on Monday morning.
Very good. Thank you very much.
Thank you very much.